What's up? I I think I'm obsessed with this soundtrack. It's just like really good. It's like all this trance music or something. I don't know, is it trance music? The soundtrack though, it's this game. Oh, you can't see anything. What's the deal? Why can't you see what's on the other monitor? Uh Hold on. How do you refresh this? I don't want to I don't want to lose its settings. Oh, there we go. Cool. Yeah, what was I talking about? Oh, the soundtrack. It's called WANT. This is like a, I don't know if this ever came to America, but it's an arcade racer game. But the soundtrack for these games are really good. But let me see if they consider this like trance music. Uh, oh yeah, just a listing. I don't know. Yeah, I don't know. Maybe I should give an update. I didn't stream on Thursday because I broke things and I couldn't get them back to working in the current project that we're working on, this BVH thing. Um, I don't remember where we left off last time, like if we actually got the BVH working or not. Um, but there was a lot wrong with it, and the biggest thing was uh, that it wasn't very like, well, it wasn't very like well written. I don't know what we said. It wasn't written for 3JS. Um, it kind of followed along with that video, that Sebastian Leg video, maybe a little too closely. This one here. Uh, this one here, I believe, with the dragon in it. Um, but I believe, I don't know what he's using. I think it's some game engine. I don't know if it's Unity or Godot or something, but um, and then when I was trying to like get ready for Thursday's stream, I just kind of broke things because the idea that I wanted to do was to make it a little bit more I don't know, well, I don't remember where we left off, but to kind of, take stock of where we were at and see how we could improve it. And there's sections in here. I think we might have gotten up to like this GPU friendly data. Um, didn't get to converting it to iteration yet, but that's something that we'll do. Maybe not today, but maybe Thursday, this Thursday. Um, but in this video, he mentions an article that he got some ideas from, and it's this one here. And this one was a little bit easier to port over to 3JS code. Um, I think it's because like the code is simpler. It's just like C code, I guess. Um, but converting this to 3JS was simpler, and maybe that's maybe part of the reason is because I got more experience doing it now. But it still isn't something that was built for Three.js. Like, it doesn't take into consideration like the way that the buffer attributes are laid out, and you know, doing things with triangles. Well, it doesn't really like accommodate for the way that Three.js does their data layout, I guess, is what I'm trying to say. So what I did, you know, past couple of days was try to convert this in such a way that would be well suited for the way that Three.js does their buffer geometries. And it was a success. And today I kind of want to show off like um, how to make the BVH and how to do it in such a way that it will be friendly towards the way that, like, friendly as in like you know, here's what we have to work with. Let's work within these bounds that Three.js has set. That bounds being like the way that it lays out data and the way that you traverse geometries and stuff like this. And the whole idea is that we want to make this, I don't know, I'm assuming at this point that people know what a BVH is, because that's like the past couple of streams have been on that topic. Or this topic, I guess, we're still on it. But the idea is that you have some scene like this one, and you want to check for intersections. So it doesn't necessarily have to be, you know, checking for intersections. Like, this is something that, like, anything that ray tracing can be applied to, this is a technique for getting like faster accelerated ray tracing. And one of those is casting a ray into the scene and seeing what you intersect with. So at the moment I have it set up where we're shooting a ray into the scene, and all of these functions and stuff are just kind of stubbed out, like just indexed, intersect. If we go over to the BVH code, a lot of these are just like empty functions that have the parameters that we'll need. So today we're going to write the body of these functions, and in the end what we should see is when we like move around the mouse, it will highlight whatever triangle it has intersected with. Now you could intersect with more than one triangle. Like, imagine like when we enter the sphere, we're hitting one triangle, and we exit the sphere, we're hitting another. But we're just going to return the closer of the two. So this intersect thing, this index intersect, returns an array of intersections. And then it's up to the caller of this function to determine what it wants to do with those intersections. That's the way that I've coded it. This is for indexed geometry, so all these functions are prefixed with indexed. And my idea there is that we'll work with indexed geometry in the beginning, and then we'll write the non-indexed version maybe on a different stream or something. But the idea behind indexed geometry is that every geometry here, this buffer geometry, will have an index attribute, and the way that you interpret that is like in the, let me make a really simple example here to show it off. Over here, so if we make a plane geometry, we got two triangles here, and the plane geometry is indexed by default. If you console.log the geometry, let's take a look at it. In the console here, try not to put my webcam in the way, but there's a property on the geometry called index right here. And the way that you interpret this is these will tell you how to index into the rest of the attributes. So you have a position attribute, a normal attribute, and a UV. This is saying you'll take the item at index 0, then you'll take number 2, then you'll take number 1. and you'll interpret that as a triangle. So I think the way that this is laid out is this is number 0. I can't remember if it's like this is 0, this is 1, or this is 2, but it's saying draw from here to here to here, and that's one triangle. And then draw 2, 3, 1. 3 is going to be this one over here. So it's probably one of these is 1 and one of these is 2, and then it's going to draw that last triangle. And that's different than just saying like having like a triangle soup and then just, interpreting the data as consecutive triangles. The idea is that you should be able to save space if you do index geometry, because not like for a couple of reasons, but one of the reasons is that your position, your normal, your UV, and whatever additional attributes you have should be all in order. The first triangle is in the beginning of the array for the position. The first triangle's normal is in the beginning, and the first triangle's UVs are in the beginning, and then it's, indexed with this index array. And you can imagine, like, we don't have to store each, like, there's savings to be had here. We don't have to store this whole triangle as a separate entity. We can just reuse some of the data from the first triangle. Namely, its index here, or its point here, and its point over here. And the index geometry is saying, like, well, we'll just reuse those points. Connect 0, 2, 1, and then connect 2, 3, 1. And the way that you traverse index geometry is a little bit, like you can imagine, it's going to be different than if you were just to iterate over all the triangles, in the array as they are. So I felt like index geometry was maybe the harder version, so I started with that. And it will have some interesting like implications for how we like complete these methods here. We'll always have to like kind of think about how we're indexing and how we're like getting a hold of that data and how we're going to the next triangle and so on. But it's not too difficult. So that's why like all these are prefixed with indexed. I think what I maybe end up doing is like changing this to indexed BVH, and then we'll have another file that's like non-indexed or something. Most of Three.js's like APIs will check for if it's indexed or not in the function. They don't separate the two. And that's probably because they're trying to be very generic and make for a good interface for, the API and stuff. I wish they would separate them. But, let's say you're given some model or whatever, you really don't want to worry about if it's indexed or not. You just kind of want to feed it into the Three.js code and say you deal with it. But not only that, but they have to accommodate for, it's not just a mesh, it might be like an instanced mesh or a batched mesh, or, might have some interesting additional information with it that you might have to handle a little differently and stuff. So they have a little bit more that they have to contend with than this like normal little demo scene that we're building. Trying to think what else before we get started. So let's just go over what these functions are and what they are intended to do. Probably pull this up. Yeah, so the way that this works is that you have, maybe some triangles out here. Like this, for example. If I just cast a ray into the scene, like imagine I'm shooting a ray directly into the monitor. The naive approach to see what you intersect with is just to, test every triangle. Did I intersect with this? No. Did I intersect with this? No, no, and no. If I shoot a ray, let's do an example where I do intersect with something. Let's say this is the last triangle that we test for. we know just visually that it's the only triangle we intersect with, but the computer doesn't know that. So the naive approach is to just test every triangle. And you have these triangles in your attribute and it's listed out like, maybe this is triangle A, B, C, and D. In the buffer attribute, it's laid out like AX, AY, AZ, and then you have BX, BY, BZ. Well, these are actually like this. This is even more granular than that. Because this X, this is actually, let's rename this. Maybe this is triangle 1, 2, 3, and 4. So it's laid out like this. 1, and then, each of these will give a letter, each of these vertices. So it's like 1A, but A is actually 3 things, right? It's X, Y, Z. So 1AX, and then 1AY, and then 1AZ, and then you have you have 1BX, 1BY, and so on. So each of these is nine entries in that buffer attribute. But you have to check every triangle, and if maybe you intersect all of them, that's cool. Maybe you only intersect one. You just checked, like, 4 triangles isn't a lot to loop over, but let's say your geometry had like 1,000,000 triangles or something. Some crazy big number. You'd be checking 1,000,000 triangles, and you'd only intersect with one. That's a lot of work just to intersect with one triangle. So the idea is that we want to speed this up. And one way that you could do that is by splitting this into 2 boxes. It doesn't have to be this box necessarily. You could split this multiple different ways. Like maybe that's one split. And maybe this is another split. Whatever. But then you'd only have to check, let's look at this example here. When I cast the ray into the scene, there's no way I can intersect with these triangles unless I intersected with the bounding box of those triangles. So if I totally miss the bounding box, this one here, or I guess we're looking at this point here. If I totally miss this box, I don't need to check any triangles inside of that box because there's no way I could hit them if I didn't hit their bounding box. And then, if I intersect with the bounding box of this set here, well, now I need to go and check those triangles inside of them, or, maybe there's additional triangles in here and maybe they've been split up like this or something. And then I would check those 2 boxes. Did I intersect with the left or the right box? Or did I not intersect with either of them? And, doing that, you're cutting down on the number of triangles they have to test for, because you totally cut out, in the first step, you totally cut out this whole graph part of it. And now you're only focused on these. But, that scales a lot better than just checking every triangle. So what we want to do is create a data structure that helps us to traverse these boxes. And of course the boxes will have triangles in them. Eventually we'll get down to, okay, there's no more boxes to check for. Now you need to loop over the triangles and check the triangles. So that's kind of the 2D case, but you can imagine this will extend to 3D pretty easily. And that's kind of what these functions are all about. Let's start at the top, I guess. We got our node, which a node is actually going to be one of 2 things. It's, in computer science, you have your tree data structure like this, You know, and each of these little circles is a node. And so a node is either going to be something that doesn't have, or does have children, or it's going to be a leaf, right? Um, so in the leaf case, that's where you'll have triangle count. The way that you can tell if this is a leaf or not, you know, is if, you know, I traversed all the way down the tree and now I don't have any more, or I guess in our case, it's going to be if the triangle count is 0, we know that we need to go further into the tree. We haven't reached a leaf of the tree yet. Once this is something that's greater than 0, that means that we're at a leaf node, for example, here. This is maybe the one that we hit, and there's triangles inside of here that we need to test for. You know, doesn't matter, whatever it is. And this left first property, that's going to be used as an index. We'll get to that later on. I can already tell that this is going to be a long stream, but I don't know, maybe we'll go quick when we actually start doing the code. This update bounds. So what this will do is it will update the bounds of the node, which has this bounds, and it's a box 3, so it has, you know, bounds in 3 dimensions. It has a left corner and then a top right corner, and that will tell you the bounds of this thing. So let's like consider it in 2D. This is, you know, x and a y, and this is an x and a y. I'm just gonna think about it in 2D because it's easier to draw, but the bounds of this is going to be, you know, this is going to be let's call this x1 and x2, y1, and y2, yeah, x2 and y2, and then it should always be the case that x2 is greater than x1 and y2 is greater than y1. So what you do is you have this like box, but you only really need to define it by 2 points. The x1, like this bottom left corner and this top right corner. And the convention or whatever, I guess, is, well, the box will have like a min, and it'll have a max property. And so it doesn't really matter, like, if these are, you know, like if this was laid out as an array, it would matter. But, you know, this is just some object with a min and a max. And then this is a vector 2. The min here would be this guy. And then the max here would be this guy. And the way that you get, like, the size of this thing is that you subtract the max from the min, or you could subtract the min from the max to take the absolute value. It's the same thing. But there's some bounds or whatever that, you know, is defined by this box 3 in our case. Like, this, you know, would extend to, you know, if this is vec 3, then this thing would be, have a z1, and this would be z2. And then same thing here, z1 is expected to be less than z2. And then you can tell, like, this doesn't store any triangles, and that's because we're going to just pass along the position attribute everywhere that we need it. There's no reason that this BVH node thing needs to keep track of its triangles. It just needs to keep track of where does its triangles begin inside of that array, and how many does it have. Or it needs to, if it's not a leaf node, so this left first is kind of doing double duty, in that you can interpret it 2 ways. It's either going to be the first position of the triangle, like, you know, this is going to be some array out here, and you've got triangle data, or whatever. It will tell you like where, and this has maybe a ton more triangles. The left first will tell you, okay, it starts here, and then you go for a triangle count. You know, left first is the first index. You know, the triangle, how do I word this? It's the first triangle's index. That's only if this thing is a leaf. And the way that you tell that it's a leaf is if the triangle count is greater than 0. If it's not a leaf, the left first will be the index of the first child. So in the nodes here, which we're going to create here, and we'll reach out into index split in this function. If you are not a triangle, the left first will tell you your left child's index in this nodes array. And again, the way that you tell if you're a leaf or not is if your triangle count is equal to 0. If it is equal to 0, then you're not a leaf. But if it's not equal to 0, and it's greater than 0, then you are a leaf, and in the algorithm, in the code or whatever, that's where we need to run through the triangles and check for intersection. And this dummy vector we'll need for a bunch of different things. I just put it outside the functions. Doesn't really matter. You know, if you had like a class or something, this would be like a field on the class. But I always thought, you know, files like this are kind of like classes in that, you know, the methods are the exported functions. The like class fields or whatever, or, you know, it's kind of just like one-to-one with a class. So that's kind of the approach I'm going with. I made this a class, I don't know why. This could also just be like plain old object or whatever, but I don't know. I don't really like classes, but if the class only holds data, then that's fine with me. There's no methods on here. That's how I like it. So index split, this will be how we split nodes, or you know, when we have a case like in the beginning, right? We're gonna put a box around all the triangles. Maybe something like this. And then we want to split this box. This index split will determine how we split this thing. This index create, that'll be, you know, how do we create the entire structure? That'll probably be where we start. And then this index intersect is assuming that it was given, you know, the nodes. You know, it's already been created, and then you're passing it to index intersect. That's where we need to check for intersection. That's being used over here in the pointer move callback. Reaching out here, so we should get a list of intersections in the end, and then, you know, we're checking for the closest intersection, and then we're setting some line geometry based on that. So that's a lot of explanation, and, you know, for reference, you can check out this article here. We'll kind of just go along with the article, and they do a lot of explanation in there as well. But I have done this before. I did it off stream, so today we'll kind of just be going through what I came up with. So the code's already there, and it definitely works. But I'll be explaining, we're just going to kind of write it out, and I'll explain what things are along the way. And I think that'll be a good, like, demonstration. But also, if I ever come back to the BVH, it'll be nice to have a VOD of this in my own words, explaining how this is constructed and stuff. I mean, like, this is like the first time that I'm coding it up. I don't think I'll ever do this again, because if I do need BVH for something, there's already libraries out there that do it, and probably do it a lot better than how we'll be doing things. But I think it'll be a good resource to have, regardless. So this indexed update bounds, again, index just means like you better pass in an index attribute. This will update the bounds of the node based on its triangle count. So you should only ever be passing, I guess. Like you're only ever going to update the bounds of this thing if you have triangles, right? So in the beginning, actually let's go here, start here first. So when we first call this thing, not here, when we first call this thing, we need to put a bounds over all the triangles, right? Where is it? But how do we know how many triangles we have? We can take a look at the index attribute. And this thing should always be divisible by 3. And that's because Three.js does, its meshes and stuff are done with triangles. There are like systems that don't use triangles. And I think there's a word for this. But Three.js does all their geometry with triangles. So if we have an index attribute, it will always be divisible by 3 because it lists out the points of the first triangle. Or I guess it's the index, right? In that plain geometry example, it was 0, 1, 2. And then I think it was 2, 2, 3, 1 or something. Maybe 2, 1, 3. I don't remember. Wait, let's take a look. Geometry. Let's take a look here. Oh, I already had it up. So it's 0, 2, 1, 2, 3, 1. 0, 2, 1, 2, 3, 1. So this is the first triangle, and then this is the second one. But it always has to list, 3 indices per triangle. If I up this to, has that, and then we do 2, 1. We take a look at this. This should now have 4 triangles. But the attribute, the index attribute, here's the first triangle, 0, 3, 1. The second triangle, 3, 4, 1. Third is 1, 4, 2. And then fourth is 4, 5, 2. So it will always be divisible by 3. And you take a look at its count. The count will tell you how many, if we take a look at the count here, count has 12. So that is, an index attribute is always like, the item size is always 1, so count here should always be 12. But you take that and you divide it by 3, that's because there's 3 points per triangle. So that will tell you how many triangles we're working with. And that's good to know because we're going to create BVH nodes that are, what is the word? Proportional to the number of triangles. So over here, the first thing we want to do is calculate how many triangles we have. And that's going to be index attribute dot count divided by 3. Right? And we want to allocate the nodes. So the way that we're going to do this is we're going to assume the worst in that, in the worst case, I guess you'll have a box per triangle. But if we have 3 triangles, let's draw this out, or let's draw it out with just 2 triangles. In the worst case, you'll have a box around every triangle. So in our example, right, when it was something like this, the triangle was like that, and then the next one was like that. This needs to be apparent. This. So we always need at least one, like root like box or whatever. And this box contains, it won't contain, but imagine that it's something like this. um, so what is this equal to? Like, how many nodes do we have here? We have 3, and that's equal to 2n minus 1. So this is coming from like graph algorithms and stuff like this. The like maximum number of leaves that you'll have, or how many like nodes you'll have in your graph, I guess. Not how many leaves you'll have, but how many nodes that you may have in the graph is equal to 2n minus 1. And I should know where this comes from, but I don't. This is just something that's done in that article. Um, let's see if they'd explain it better than I can. Oh, this is number 2. I want number 1. Where is it? Yeah, right here. We can do this because the size of the BVH for n triangles has an upper limit. We can never have more than 2n minus 1 nodes. Since n primitives in n leaves have no more than n over 2 parents, n over 4 grandparents, and so on. So, this is how many nodes we'll have. So we'll pre-allocate all of these nodes. And these nodes, I'm going to put it in a separate function because I think this will be the same. Actually, I know this will be the same whether the geometry is indexed or not. So we'll create nodes of size n. We don't have this function yet, but let's make it. And it'll take a number here. I'll keep putting it under index split. It should go under index create. So, you know, just when stubbing this out, the nodes was an empty array, but now we'll return whatever this returns, and it should return array of BVH nodes. So something like, you know, something like this. But we actually need to create 2n minus 1 of these. So we'll return a new array, and we'll actually do array.from length of n, and then here we want to return, oh sorry, it's not n, it's 2n minus 1. But I think, yeah, it should be n. What I want to do instead is pass 2n minus 1 here. 2n, yeah, minus 1 there. And then here we'll create a new BVH node like this, and we'll return that. You can't do this, so this is kind of like a side note. You can't do this because what this will fill the array with is references to the same BVH node. You have to kind of create one like this. So everything in this array here will refer to the same node, but these nodes will have different triangle counts, and they'll have different bounds and so on. We can actually get rid of that return there and do it like this. So now we have our nodes. So if we log out the nodes, we should see let's see. Where did we return the nodes? Right here. I think I had another, yeah, let's not log the geometry at the moment. And then let's do a simpler case. So yeah, this is our 3 nodes, and that lines up. Well, of course it does, because we've got 2 triangles here, so 2n is 4, and then minus 1 is 3. So if we bump this up to be like this many, I think this will be 8 triangles. 8 times 2 is 16, minus 1 is 15. And you got 8 triangles here. You got 1, 2, 3, 4, 5, 6, 7, 8. So that kind of like, you may not use all of these nodes. Um, and I think in the later parts of that article, they'll talk about, how to only allocate what you need. Probably especially when they switch over to doing it on the GPU. But we're not there yet. So now we have our nodes nodes allocated. The next step is to create a box around all of the triangles. So the first node in the array is going to be like the root node, and that will contain all of the triangles. It won't, once we start splitting up that node, it won't contain any triangles. Its triangle count will be 0, but in the beginning, that's where, it will be the only node and it will contain all the triangles. So what we need to do is pass this thing, here's the root, but we need to set its bounding box properties and triangle count and all that. So the triangle count, we know that this thing should contain all the triangles. Its triangle count should be equal to n, right? That makes sense because we've got, 2 triangles here. It should contain 2 triangles. Well, we calculated it right here. So it contains 2 triangles, but we need to update its boundary, or its bounds to, contain those 2 triangles. And that's where the indexed update bounds will come in. So this thing will take the node, which is actually the root, the position attribute, and the index attribute. And it will modify properties of the BVH node here. Let's get rid of that console.log. So we need to do that here in the array, or here in the function. We need to loop over the triangles, and we need to expand this boundary, this bounds, this box 3, by each triangle. So to loop over the triangles, I is less than, what is it? Oh yeah, it contains all the triangles, so, it starts at 0. This thing defaults to left first of 0. And then how many triangles do you have? Well, we have 2 triangles, so we set this before we made that function call. That was equal to 2, so we're looping over 2 triangles here, right? It should go 0, 1. So we just increment I by 1, and that will give us the index of each triangle. So 0 and 1. But the actual index into the buffer attribute, or yeah, this is the index attribute. You remember that each of the, like, these things come in sets of 3, right? So the actual index, that's going to be equal to 3 multiplied by, where do we start? We start at node.left first. And then we're going to add I. So how do you read this? Left first is going to be 0 in this particular case. I starts at 0. So if we were to put the debugger here, can you see that? Yeah. So when we hit this debugger, I is going to be 0. The left first is going to be 0. And then, 0 times 3 is 0. This will be equal to 0. If we step, where's the step? Right here. So, oh, we don't, well, index will be 0, right? you know it'll be 0, because 3 times 0. Next iteration, I is 1, so this will still be 0, right? We haven't changed that. And then 3 times 1. So that went from here. So this is 0, 1, 2. This is the actual index itself. It went here, and then it jumped to here. You know, because this is the first triangle, and this is the second triangle. And if this was starting at, you know, if we had more triangles in this thing, and we weren't actually the root, but we were something deeper in the tree, we would offset to the left first. That will be the starting position, and then, you know, the I is how many triangles we're looping over, or the like triangle index from there, and then we multiply it by 3 so that we're skipping over each of these. So that's the index, and we take the node bounds and we expand by a point. And so what is the point? We're going to use the dummy vector for this. And so this is a vec3, but it has a property called from buffer attribute. And what attribute are we looking at? We're looking at the position attribute. And then we can get the x. Actually, we don't need to get anything, right? Because this will read 3 values from that attribute, but it needs to know the offset. Yeah, the index. So the way that you do this is you look at your indexed attribute, and you need to get the x that corresponds with... So this is weird. We're using an index into an index attribute. But, you know, I here is equal... Actually, this is index. Let's save it so it formats. Index here is 0, so the index that we're looking at, this corresponds to this guy, right? I here, this is the actual index. Oops. It's the actual index. Once we get the x, that's like saying, you know, don't add any offset into this, and it will handle, like, if the attribute array is normalized or not, and so on. But you can just imagine this as kind of like, you know, pointing to here. And then, you know, in our case, right, the index here only takes on 2 values because we have 2 triangles. It takes a value of 3 in the beginning, and then when I is 1, it takes a value of 3. So we kind of skip over these indices, and we should, because, you know, these correspond to each, you know, these are kind of, think about these as like sets or whatever, right? So yeah, we get the x. This will say, okay, start at position 0 in the position attribute, or index 0. And then pull 3 values off of there and then put them into dummy vector. That's what from buffer attribute is doing. So that's expanding it by the x. Or sorry, that is expanding it by the first triangle. No, it's not. Let me think about that. By the first point, that's what it is. Yeah, expand by point. So let's say like this triangle is something like this. This is the first point here is this. Or sorry, is this thing... This is hard to think about because you have so much data that you're kind of juggling, right? So this will be a pointer into that position attribute. You know, this is the index array or attribute. That's ATT for attribute. This is, you know, a pointer into the actual position attribute. Right? And then we need to expand by, so we only did this point here. We need to expand by this point and by this point. So it's going to be the same code, but the offset, or the index will be different. So we can grab this. And instead of doing get x, which pointed to this one, now we need to point to this one, which is get y. And that will really just add 1 to this index. It'll jump here. And then we do the same thing, but for the z. And then expand by point, yeah, it returns the box 3, so we can just kind of chain these together. There is no expand by triangle on this thing, but you can imagine this would be like if you were to make your own function that did that, this would be expand by triangle. What's highlighted here. So that's kind of that's all there is to this function here. Now when we expand by bounds here, or we update the bounds of that node, we should now see it in the code. We turn the debugger off. And we make it visible. It's this yellow box. So there is no depth to this thing because the plane geometry doesn't have any depth, or its z values are equal to 0. But if we turn this into a sphere geometry, it should have a box around the whole sphere. And it'll work for any geometry that we put in. So this is like the very first step. And then we're going to recurse on this thing. We're going to like, keep going until we hit some condition. We're going to keep splitting this root BVH node until we hit some stopping condition. And we'll talk about that when we get there, but it doesn't matter what geometry you put in here now, as long as it's indexed, it should work. And I think this one is also indexed. Yeah. Let's keep the simple case. So that's the plane geometry. So that's how you update the node's bounding box based on its triangle count and its left first. So pretty simple. The difficult part is keeping track of, the indices here. But now that we have a single root to work with, this is kind of like the entry point into this bounding box, like this BVH construction. Down here, we've updated the root bounding box bounds and stuff. The next thing to do is to set up its left and right children. So its left index here it is. Actually, we're kind of done here. Then we call index split, and we pass in the root. So we'll get to this function next. The root, the nodes, the position attribute, and the index attribute. These getters, I don't know, these getters are, you'll see how these are going to be used in a moment. But then we need to split that root node, so that's the responsibility of this function here. So the index split, that's like saying, okay, I want to split the parent into two separate children, right? We've already allocated the BVH nodes for that, so we don't need to create anything, we just need to modify what's already there. So you can imagine, like, there's no real like construction here going on. It's really just setting up all of the like indices and all of the properties and stuff of the BVH nodes that we've created before we called these functions. So the nodes are already there. We're just kind of like modifying all the data that's involved so that we can interpret it as a BBH. Interpret it, and then we can loop over it. Here, when we do the intersection checks, we can, the data is set up in such a way that we can easily like loop over it and check for intersections and stuff in, such a way that it should be faster than just checking every triangle. So it's a lot of data manipulation. So in this function, we go up to the other monitor here. So let's consider our stopping condition first. In the article, like, they stop when the triangle count is less than 3. So that means every leaf node will have 2 triangles inside of it. So we'll just return from there. That's going to be the stopping condition. This has to be at least 2 triangles, I think. There's a reason for this, and that's because of how we're doing the splits, I think. But maybe I'll remember when we get there. But if you wanted to keep more triangles in there, you would just increase this number. So that's going to be our, that's where we're going to stop calling index split. So, later on we're going to do index split again with some other parameters. And we're going to do that for the left and right sides. But those won't keep recursing, and if this is true, right? We don't call these things again if we've returned early. So if we still have triangles that are, greater than 3, that's where we need to split. We actually do the split of the node. So we'll get the size of the node, and splitting is something that we're just going to take a naive approach to in the beginning. There are more thoughtful ways you can split the node, but we'll just do what's done in that article in the beginning, which is split up by the maximum. It's either the maximum or the minimum axis. I think it's the maximum axis. So that may not always be the best split, and the second part of the article talks about how to get a better split, but we won't focus too much on that today. I think that's what we'll do on Thursday, is we'll use what's called a surface area heuristic, which is talked about in the article, and that will give us, or it should give us, maybe at the cost of a slower construction, we will get faster intersection queries. But again, like, I'll kind of describe that when we get there, probably on Thursday, if I can finish it all today. So we need to get the size, and the reason why we get the size is because we need to know where we're going to put these triangles. We're going to split this bounding box. Maybe it's something like this, right? We had a box that contained these triangles, and we want to split it like this. So how do we know what side of the split do these triangles go on, right? This is what we have before the split. Once we split, we need to know, okay, what side, do I put this triangle on the left, or do I put it on the right? And the way that you tell is that you need to check its, whatever axis we used for splitting. Here we just use the x-axis. We need to check its x position of, each of these things with the x position here. If it's less than that, then we put it on the left side. If it's greater, then we put it on the right side. Imagine the number line here, and then this is at some position, right? These things also live on the number line like this. Each of these points. And we're just saying, like, put them all on the right if they're greater than that X position, put them all on the left if they're not. But it's a little bit more interesting than that, because what we'll do is we'll actually shuffle around the triangles inside of the actual buffer attributes. But the first thing we need to do is we need to get the size of the bounding box, because we're going to use the maximum axis. So we do node.bounds.getSize, and again we can put it into the dummy vector. Dang it. And then we need to get the axis, so we'll say axis, that'll be an actual like index. And there's three axes that we're considering, right? The X, the Y, and the Z. So we'll default to 0, but if the size.y is greater than size.x, then the axis will be 1. And then if the size.z, this is checking if the y-axis is greater. If it is, then set the axis to 1. If the z is greater, then we'll set it to 2. So what goes here is going to be the size.get component, and we'll get it by its axis. So we can't do like size.y here, because we don't know here if, all we know is the index. We don't know if it was the x or the y. We don't know what property it was. We just know the index, 0 or 1. But this get component function takes the index and will tell you, if index is 0 here, it will return size.y. If it's 1 here, it will return, or sorry, if it's 0, it'll return the x. If it's 1, it will return the y. But if this is true, then we need to return 2, because the z and z axis is the greater one. And then the position, the split position, what we're going to call, that's equal to node.bounds.min. So each of these bounds has a min and a max. We need to get the component for that axis, and then we add on to it half of the size.get component of the axis. So this is going halfway into the bounding box, right? So this is the min over here. This is the max over here. So we start here, and then we're going to add to it. Well, this is only one dimension, right? This thing just returns a number. So yeah, it is just the x, and we're going to add to it half of the size in that axis. So the size here, is some size for this whole length here, but we only want to go halfway. So that's, add to it half of the size in that axis, and that will get us here. And that will be our split position. And it's one dimensional, so it's not a position in 3D, it's just, one dimensional position along the x-axis. Could be the y-axis, could be the z-axis, but in this example, it's the x-axis. And then what we need to do is loop over the triangles and put them either on the left side or the right side of that axis. So I'll set up the code real quick, and then I'll explain it. So let's see. I'm not going to save this because it'll make an infinite loop. But we'll start wherever the first triangle is, and then we'll go up to we'll go up to the number of triangles that we have from that. So these are the indices, right? I want to stop short because we don't want to go like, this is an off by 1 kind of thing. And the length of this, let's take the case where all the triangles are in the node. So we got 2 triangles here. Actually, let me draw it like we have in the example. Two triangles here, right? The first index is 0, and then the triangle count is 2. So with 0 plus 2, that's 2. But if we try to index into the position attribute and so on, if we don't subtract 1, we'll go out of bounds. And that's because, you know, imagine any JS array, right? The length of this thing is 3, but the last index is 3 minus 1. Right, because it's 0 indexed. So it's the same thing that we're going to do here. I want to subtract off 1 here so that we don't go beyond the bounds of the attribute or the array. Then we have two things that we need to check. Well, should I show that or go do that? This underscore I, so remember that the index attribute is, you know, sets of 3. So we need to multiply I by 3. Anytime that we're getting a value from this left first, we need to actually multiply it by 3, which happens here and happens here. And then here's where we're going to use the getters, these things here. So the 0 position corresponds with the x-axis. Or let me think. Oh yeah. So the getter here is like, you know, we're getting into that position attribute. If it is the x-axis, we need to get the x of the point. If it's the y-axis, we need to get the y of the point, and so on. But again, same thing that we did here. These indices we can just use to get out a function that we can call. So the getter, we're going to index into getters by the axis, and then that will be the getter. Here this will be a function. Oh, it's state.getters. We do it in a state because we don't have to create these things every time we call the loop. Well, I guess we are creating this state object every time. No, we could just pass state through. Yeah, never mind. So I'll show that at the end of the loop, how we actually pass this along. So this getter is saying, like, am I getting the x of the position or the point? Am I getting the y of the point? Or am I getting the z of the point? And it's based on whatever axis is the maximum axis. So here, you know, we'll do getter, but what do we pass in? We pass in an index, and we need to look into the index attribute, get x of underscore I. That means, right, that, where's the drawing here? The underscore I is 0 and 3. So, you know, 0 says, you know, this maps to 0, that's to get x, and then the getter says, okay, you want to get the x of that point. And it's the same thing for getting the y. So this is y now, and this is 2. And this is z. So this is kind of confusing. It's the same problem, right? You have 3 like indirection steps. 3 or 2, I don't remember. But this is like, you can kind of trace these along, and the way that helped with me, and I might make a diagram to help demonstrate what this is actually doing. But the triangle, you have like your triangle indices, you actually have your index attribute, and then you have your position attribute. So your triangle indices will tell you, you know, how to offset into the index attribute, and then the index attribute will tell you how to offset into the position attribute. And this is only because the geometry is indexed. It will be simpler for a non-indexed geometry. Maybe that's what should have shown off on stream, but at least this will be a simple, like when you, if you are dealing with non-indexed geometry, this will be simpler because you don't have to worry about the index attribute. You can just assume that triangles are laid out consecutively in the position attribute. But these are the points of the triangle that we're considering, and we got them from the position attribute. Remember, this getter is this getter is, you know, accessing this position attribute. So it might make sense to be like position getters or something. Something like that. But there, like, this is not the triangle. I think I misspoke. This is not the triangle. This is the it's the x coordinate of each point of the triangle, or it's the y coordinate, or it's the z coordinate. It depends on what axis is. So we're taking the triangle. I need to redraw it because I lost it. This is, you know, ax, ay, az here, but we're only considering the x part of it. What we need is the midpoint of this thing, and I think I might have misspoke again earlier. We're actually not taking every single point, but we're taking the midpoint of that triangle and asking if it belongs on the left side or the right side. So the midpoint, that's equal to each of these added up, and then divide by 3. And this is the midpoint for, you know, anything, right? Midpoint is always you take the 2 values or the 3 values or the n number of values and you divide out by the number of values. So it's the same formula like if you had 2 numbers, let's say 3 and 9, right? Where's the midpoint? Well, you add them up and you divide by the number of data points that you have. So the midpoint here is 12 over 2, or is equal to 6. It's the same thing in 3 dimensions. Or not dimensions, I should say, whether you have this many data points or whatever. So we've got 3 data points because it's a triangle, and we're just finding the midpoint in the x-axis. I keep saying x, but you know, this could be the y or the z, whatever is the maximum axis. That's the midpoint. And then we need to say if that's on the left side, oh, yeah, I remember now. So if it is less than the split position, let's handle that. Then all we need to do is increment I. If it's not, then we'll do something else. So why is this the case? Well, we're going to assume that all the triangles that belong on the left side of the split are going to be towards the left side of the array. And then the ones that belong on the right side are on the right side of the array. So this is starting at the left side of that, it's like subarray. If it's already less than, you know, it doesn't need to be moved to the right side if it's already less than the split position. Right? And it doesn't matter if these triangles are sorted by their x position, as long as they are on the left side of the split position. So all we need to do is increment I. So yep, that triangle is okay. That triangle was on the left side and it belongs on the left side. So we just go to the next triangle. If it's not, then we need to swap it with something that's on the right side. So if, this is some big array, right? And then we're looking at, we have triangles over here, but this thing is somewhere right here. And here's our split position. And we're looping over, here is the first index, or the left first, I guess it's called. That gets us right here. And then this thing here is left first plus the triangle count. So let's do like LF plus the triangle count. These are not like sorted by their maximum axis, yeah. So we're looping over the triangles here, right? And then we only, like, if it was on the left side and it was already, like, if it was already on the left side and belongs on the left side, we just need to add 1 here. That's the I plus 1. And we go to the next thing in the list. If it needs to be swapped, we have a pointer to the last thing in the list with this J. And we need to swap it with the last thing in the list, and then we decrement J. Because we found that that triangle actually belonged on the right side. But if we start on the right side and we go this way, everything on this side should be the right side of the split. So we're kind of just moving along, like we're swapping things. X, Y, Z, whatever. And we don't know what's out here, but we're going to swap it there. And we're swapping in such a way that when we do the swap, like, we'll check this one next as well. Right? I don't like how I explained that, but the idea is that we're putting everything that belongs on the left, everything that belongs on the right, on the right. And we don't, like, it's not sorted by anything. We don't know, we just have some triangle list, and they're not sorted or anything by their maximum axis at all. But the way that we do sort, we're gonna make a helper function for this. I'll pass in the actual array and then the offsets. And we'll do j minus equals 1. So that's moving this side to the right by 1. And a stop condition for this loop is I is less than or equal to j. So as we loop over these triangles, like, I'll go this way, j will go this way. Eventually they'll overlap, and that's when we stop and say, okay, it's now been sorted by their, or at least swapped around by their maximum axis. Let's write this swap function. So it will take in a typed array, which I think T actually has a typed array. It'll take an I and a J and a count. Okay. So this is swapping triangles, but they're not stored as triangles. They're stored just as, numbers in some buffer attribute. So what we need to do is accommodate for all of that, and that's why we're multiplying this by 3. But because these are laid out, like the triangles are laid out, you got 0.1, 0.2, 0.3, and then you got 0.1's XYZ, 0.2's XYZ, 0.3's XYZ. So that's why we're multiplying by 3 here. This is not the index attribute, or is it? Yeah, it is. It is. It's not the position attribute, and the reason why is because we're not really modifying the position attribute. That's just like, here's the data pool. Index attribute tells you how to draw these triangles. So modifying the index attribute is like modifying how we're drawing these things. And the index attribute, do I still have it somewhere? I'm sure it's somewhere on this canvas somewhere. Yeah, right here. Here's the index attribute. So we actually just need to swap around indices. But we need to swap them around in sets of 3, right? So we can't just swap this with this. We have to swap that entire triangle. It's 2, 3, 1 in this case with this guy's 0, 2, 1. So we're swapping like sets of 3 around, and that's because every triangle has 3 points, and this thing says the triangle is defined by 0, 2, 1. This one is 2, 3, 1. If we want to swap these two triangles, we have to swap all of the indices that correspond to that triangle. So the math behind that, I just had, the AI do it, but it makes sense. We take a slice of the array that's starting at I and then ending at I plus the count. The count here is 3. This probably should be hard-coded at 3, but that's okay. And then, so we have a temporary array, and then we overwrite what's in the array with a subarray. That's, the J. The J is some other triangle, starting position, 3 units, because the triangle has 3 points. So we overwritten the position at I with that triangle. So this, here, if we take this, for example, this is triangle 1, this is triangle 2. We saved this into a variable, that's the temp. So we saved that into a variable. We overwrote, we overwrote this with this information. And then we need to overwrite this with that temporary variable. And then reading this back out, dang it, that's annoying. Yeah, 2, 3, 1. So reading it out left to right, 2, 3, 1, 0, 2, 1. That's what this is essentially doing. Normally when you swap, right, you're only swapping one index with another, or one value in the array with another at some index. But now we need to keep these grouped together, in sets of 3, right? So the count is like 3 in this case, because we have 3 points that we're dealing with. The index attribute refers to like 3 items. So that's, and the reason why we're doing that is we're swapping the triangle on the left side with something on the right side. If it didn't need to be swapped, it belonged on the left side, then we don't do that. But this is, modifying things inside of that array, inside of that typed array. So that's looping over the triangles and putting them on their correct sides of the split. The last thing we need to do is to update properties of the bounding boxes, which we already allocated. So this is modifying the triangle data. Now we need to modify the node, like the BVH node data. So the left count, that's how many triangles are on the left side of the split. That's going to be equal to I minus node dot left first. I here was, modified in this loop, so we're going to reuse it, which is nice. So, I started, maybe it started at 0 or something like that, but it increased. So it started at node dot left first, but it increased, or maybe it didn't, it depends. But every time we entered this side where the left didn't get, like, we just incremented I or whatever, I went up by 1. So I should at least be equal to or greater than node.left first. So that's number of triangles on the left side of the split. And the left index that's going to be equal to amount of nodes used. So we do have this like state property of the nodes used. It starts out at 1 because when we set up this indexed create, we utilized one node of the nodes array. That was the root node. So state nodes used starts at 1. That accommodates the root node. This is going to be state nodes used, so that's the, let's draw it out. So in that really simple case, right, this thing, we had one whole node, that was at position 3, or sorry, position 0. Why did I say 3? Right here. And then the amount of nodes used is 1. Right? This is the next position, so that's nodes used 2, and then that corresponds with 1. So yeah, okay. So the amount of nodes used is 1. That'll actually be the same as this position here, right? So the left index is the state nodes used, and then because we set the index, we say, okay, state.nodes used gets incremented by 1. But before we do all that, we need to check, this will be another like way that we can terminate the loop or the recursion, is we check if there's no left count, and then so this is saying that we didn't put anything on the left side. If we didn't put anything on the left side, then we don't need to do anything. If we didn't put anything on the right side, we don't need to do anything. Well, at least this part is saying we didn't put anything on the left side. And that happens when this returns 0, right? Where we didn't increment I at all. This is saying we put everything on the right side. I believe that's what this is saying. So that's when this is equal to triangle count. And when does that happen? That's true if this is true. Right, this will reduce to node.triangle count. So this is the I. I don't know, that's hard to explain. But essentially, this, let me refer to the article to see what it says about this. So it's this check here. This is the easiest article to search through. I don't even remember if it talks about that. This thing here. I guess that's what this is. You know, every time they're like, I don't feel like doing it, this is what they say. Left as an exercise for the reader. Oh well. Left as an exercise for the viewer. That's what I'm gonna go with. Okay, so the left child index, state.nodes, or state.nodes used, and we increment. And the right, or sorry, the left, that's going to be nodes at left child index. So we have our left child. The left.left first is equal to the node.left first. Right, it just inherits that. And its triangle count is equal to I. That's the amount of times we incremented I. On the right, that's nodes at left child index plus 1. The right index will always just be left child index plus 1. The right child index so I guess we could use, yeah, we could either do left child index here plus 1, or we can use, because you know this is the same as this plus 1, which is this. But we need to increment the state either way, so I guess it makes sense to do it this way for the symmetry. And then we'll increment state.nodes used. This is nodes at right child index. And same thing, we need to modify its properties. So left first is equal to node.left first. Oh no, sorry, it's node.triangle count minus left count. And it should always be the case that the left count and the right count equal the triangle count. We're not storing the right count anywhere, but the right count is equal to this. Or sorry. Yeah, I have this backwards. It's equal to I, and then this is triangle count. Okay, let's look at this for a moment. So we want to get the left and right child. That is going to be how we're splitting up the current node that we're looking at. We sorted the triangles. Triangles sorted. Next thing we need to do is update the left and right child. The parent node has already had its left index set. No, it hasn't. there's a little bit more to this. And then let me just get this on there and then I'll try to explain it. Index split, we'll do left, nodes, position, attribute, and pass along the state. And we'll do the same thing for the right. Okay, so let's talk about this. We updated the triangles. Now we need to update the children nodes. There's only two children, the left and the right. Here we update the index, the triangle count of the left. We update the index and triangle count of the right. And then we update their bounds. We have the left and the right from here. So we already wrote that update bounds function. And then we keep splitting, right? We're going to keep splitting until we either return here or we returned here. So now we split on the left and the right. When we come back from all that, what we need to do is set the left child. So left first, remember this is either going to be the first index of the triangles, if it's a leaf node, or it is the left index of the left child. It's so confusing. And then we set its triangle count to 0. This is saying like, yeah, that node has been split. It does not contain any triangles. So that's the split function. That's part one of the two hard parts about this. If I wrote it all correctly, we should see when we view the boxes, something that's a little bit more abstract. Okay, we only see one box. Did I call indexed split? I did. I gotta see what went wrong. That's right. That's all right. I think we're okay. I'm just not sure why we're not seeing more than one split. If we go over here, yeah, that's weird. Ugh. Should have seen a lot more nodes than that. So this is asking, you know, like what nodes contain triangles? How many leaves are there? We should see a lot more than just 3. So let's go here. You know what? I'm lazy. Let's just copy and paste. Left first. Where? Where's the error? Left first. Okay, here's what I'll do. I'm not sure where that error is. I will copy everything except for the indexed intersect. And hope for the best. Wait a second. Oh. We want that, we want all that. Yeah. Okay, I don't feel like I explained any of that very well, but there's plenty of resources out there if you want additional information. What don't you like here? Node is not iterable. What? Why didn't you copy that? Oh, duh. This is, I don't know why, but it did not save it properly whenever I modified this. Okay, let's see if the bounds, yeah, there we go. So I'm not sure what, that's kind of the difficulty with copying and pasting, not difficulty, but, you know, trying to code things one-to-one with something on the other monitor is like, you might miss something. But I mean, I always prefer people to do like live coding rather than just like slides of code or whatever. I try to avoid that. So yeah, I'm not sure what was wrong, but this is the correct thing that we should be seeing. What we're seeing here is every node that does not, or every node that has triangles inside of it. And that makes sense, right? We'd expect it to be pretty symmetric. If we increase the number of allowed triangles, let's go like 10, we'll see a lot less bounds. Let's go up to like 20 or something. So each of these nodes has at least, or I guess at most, 20 triangles inside of it. But we can all go all the way down to just 2 triangles. And I guess the reason behind that is that if you try to split a node with two triangles inside of it, you're going to end up with one triangle in one node and one triangle in the other. And at that point, you're doing more work when you try to intersect, because before you only had to check two triangles. Like you made it all the way to the node and you only have to check the two triangles inside of that node. If you had split that node, you'd end up with this situation. So before the split, you had a node, right, with two triangles inside of it. When you split it, then you had this situation. Intersecting with this is probably, yeah, it is less work, because here you check one node and two triangles. Here you check two nodes and two triangles. So that's kind of the reason why, you know, if the triangle count is less than 3, or, you know, you had two triangles in it, one or whatever, splitting it up is going to do more harm than good. Not harm, you know what I mean. It's going to be more work. So yeah, let's do the last little piece here is going to be the actual traversal, and then we'll call it a day. Explaining this stuff is pretty difficult. But try to explain it in relation to Three.js and why we're doing all this weird index juggling and stuff. But the intersection code is fairly straightforward. Like the split code is the hardest thing to explain. The intersection code is actually not too bad. So here we've got the node index. We're going to pull off, you know, whatever node corresponds to that index. We're going to check if that node has triangles, meaning that its triangle count is greater than 0. We're going to loop over those triangles. Why did I say intersections here? This should be node index. I'm losing it. Okay, so loop over the triangles. Again, anytime we get from the triangle count, we have to multiply it by 3. So the actual index is 3 times node.left first plus I. And then the intersection, we're going to test ray.intersect triangle. Here it takes in 3 points, but we need to get those points from the position and index attribute. So it's kind of the same thing from the split from earlier. Well, not the split actually, from this. But we need to keep we can't just use dummy vector, we need to keep these separate. So it's the exact same thing, but instead of dummy vector, we need to keep each of them, like not overwrite dummy vector each time. We actually need to keep A, B, and C from, you know, separate from each other. So because it's the same, I'm just going to copy and paste it. And then we have, I won't go over what these parameters are. True, and where do you want to put the intersection dummy variable. So that's our intersection. It could return null, indicating that there was no intersection. In that case, we'll just continue the loop. That says we did not intersect with that triangle. Otherwise, we'll calculate the distance squared from that intersection to the ray's origin. And then we'll take the intersections, we'll push onto a new intersection. Triangle we already have. That's A, B, and C. And the reason that we're cloning these is that these are taken by reference. So we don't want to override other triangles A, B, and C. That's what would happen if we just continued here with the loop. Let's say we made a triangle. If we were to just use these without cloning them, next time we do this, we'd be modifying every triangle that we created. We'd be modifying its A, B, and C. The point, same thing, we don't want to update or modify existing points, so we clone this thing, and then we just pass along the distance squared. And then let me alphabetize these. And then the end of the loop, we're returning the intersections. So that's kind of all there is to it. To go over it again, looping over the triangles, we're getting the position information for each triangle, putting it in the dummy vector. This will return null if there was no intersection. In that case, we just continue in the loop. If it did intersect, then we need to make an intersections object out of that and push it onto intersections. This is creating clones because these things are passed by reference, and we don't want to modify if we did pass them along like underscore A without cloning it and B without cloning it and so on. Whenever we do this, we'll be overriding those triangles A, B, and C. So I think if I set this up right, we'll come back over here. I'd expect this to work, but let's see if we get any intersections. No, it's returning nothing. So I think I made another mistake somewhere. Oh, yeah. Yeah, I didn't copy all my code. That's frustrating. So there's a trick in NeoVim. Like if you forgot to commit something and you still have NeoVim, I don't know if it saves it. Yeah, it does. NeoVim keeps a history, or Vim keeps a history, right? So you can do earlier. We can go back like, how long has the stream been? 2 hours almost? We go earlier 2 hours. Let's go even further than that. Let's go earlier 1 hour. This was before I started the stream. This is what was in the file before I like got rid of all the body of the functions and stuff. But I did make one change that is significant. Oh, yeah. Let me fix this real quick. So we got distance squared. That's a number. Is this? This was dummy vector distance squared array dot origin. Okay. Does it work? Yeah, there we go. So let's not log it. This is what we want. It took a while to get there, but this is working. And it's returning. I guess it is returning only one intersection. Might be how we're you know, looping over or like traversing over the nodes. I'd have to think about that. So this is it. I don't know if I'll go over this again, but it takes a lot of thought, you know. It takes a lot of drawing it out, and maybe it would be more helpful if I created visualizations for all the indice jumping around index, you know, attribute modification and stuff, the data manipulation and all that. That's what most of this is moving data around inside of these buffer attributes and stuff. Would that be interesting to do that? I don't know. Maybe. Maybe it would be something worth doing. Yeah, I gotta wonder, like, how I've been looking at this kind of code for so long now, and dealing with this BVH stuff, that things that look kind of simple to me, or straightforward to me, they didn't in the beginning, but now that I've been working with it so much, I can kind of see the big picture and understand why things are happening. And I think, you know, one of the characteristics about being like a teacher or a good teacher or whatever is not assuming that, you know, these people have seen any of this before. But then it's like you don't want to go into the nitty gritty of everything because then we'll be here all day. You know, like you got to make some assumptions about the prior knowledge of the audience. And I guess in cases where you want to go deeper into something, you would provide like resources or refer them to some other kind of information, right? Like, you know, all that supplemental content kind of thing. I don't know. I feel like explaining the shader stuff. So in the past, right, when we were working on like the post-processing stuff, these things, I feel like these were easy to explain, but this BVH stuff is not very easy to explain. Like even this one was easy to explain. The things that we've done on previous streams. Like this one. So I don't know. But I think, you know, this is probably the most difficult part of this whole operation is the beginning. Once you have an understanding of like why the data structures are set up like that, then I think it'll be easier to follow along. But from here, the next step is to optimize some of this stuff. So there's a couple of places where we can optimize this. And one of them is how we're doing the splits, and I kind of talked about that earlier. Um, we can be more thoughtful about how we're choosing a split axis at the cost of a little bit more time to construct this thing. Um, it would be cool to do like real-time BVH construction, but it would have to be so fast that you could do it like, you know, 60 frames a second or something. And I don't know if I'd have to look at some. I'd have to do some research and see when you do 60 frames per second, like BVH stuff, are you modifying what's already there? Or are you creating the BVH from scratch every time, every frame? Um, I wonder if there's ways to get around creating the entire structure every single time. But that's way down the line. But I think it'll be interesting to see if that is true or not. Let's see. So that's one place we can save or be more optimized is where we split and how we split. Another thing is, doing recursion like this is not very friendly for multiple reasons. For one, you could have a case where you reach the maximum call stack, but typically, I don't know, 100% of the time, you can convert a recursive algorithm into something that uses a stack. So that's probably what we'll do. I think that'll be the two things we do next stream, probably on Thursday. We will do the SAH. Where is it? The surface area heuristic for, yeah, this thing here for how we're doing the splits. And the other part may be the converting it to use a stack instead of doing this recursive algorithm stuff. And then we'll see where we end up from there. And I also want to kind of make better visualizations for this stuff. But, you reach a point where you're like, I'm kind of tired of doing BVH stuff. And I don't think I'm there yet. But, we'll see. I get kind of bored with these topics probably too quickly. And that's probably why I haven't worked on a very big project for very long. Like, I don't have, like a game or something that I'm developing. It's probably because I'd get bored of that game very quickly. Or not bored of the game, but bored of developing on that game. Um, so, is that the end of the album? No. Oh, this is a whole new. So Spotify does that thing where it was the end of the album, probably a long time ago, but they just continue playing music. So I might get DMCA'd or something for this music. I gotta turn off autoplay. I wonder how many songs it played. Okay, I think I'm going to end the stream there. Um, Not really satisfied with how I explained things, but maybe the code can help out. And the code, at least in this stuff here, I will eventually put on the GitHub. I might do that today, later today. Because it is, I would say it's very different than what's in the article, but it does kind of do more thoughtful stuff with the buffer attributes. So it's built for Three.js, right? It's supposed to be used with Three.js. So I think it'll be a good resource to have for people that want to look at it and understand it and, um, do things with it, whatever. I don't know. Okay, so next stream will be Thursday. I guess that's it. Hope everybody has a good week. Today's Tuesday, right? I'm gonna go get a chicken sandwich. And I feel like I've said that before, but I just love chicken sandwiches. And it's right across the street, so I'm just gonna walk over there. And my car is in the shop right now. Because the AC is kind of not working as it should. Uh, so they are checking it out, but I told them to take their time because I don't need the car because I'm not working today. So hopefully they fix it and it doesn't cost me any more than they already said because it was already kind of a lot for them to do some work on it. But I'm the only one that ever drives that car and it's the only one that is ever like using it and I can deal with no AC. The car is really old too. It's like why put any money into it? I mean, it would be nice if the air conditioner worked, but like I go to work so early in the morning that it's cool when I go to work at like 4 o'clock or something in the morning. Um, it's not very hot at that time of day. It does get hot when I'm leaving work and I'm coming home, but I just roll down the windows and it's fine. So I've already kind of committed to them doing the work that they've are doing today, so I'll have to pay that at least. Um, but if they want to do any more than work than that, I'm gonna be like, I don't think it's worth it unless it's like $100 more or something like that. I have a budget. So I will see you guys on Thursday. Thanks for watching if you're still here. Thanks for tuning in if you've already left. Um, yeah, I'll see you guys Thursday. Here's where we switch scenes and we do this and we do this. And we turn off the microphone.